Okay, in Unit 7, Lesson 4, we're finally learning how and why logarithms are still so important. We can solve any exponential equation. That means an equation where the exponent is unknown. We learned when we were in the exponent chapter of how to use a method of common bases. We'll review that for a second. But what happens if we can't find a common base? We then what's called the third log law. You really don't have to know that. You just have to understand how to use it. And of course, we'll show you that in a few seconds. So for example 1, in the exponent chapter, if I gave you 4 to the x equals 32, by using common bases, you would say, oh, well, I know the common base here is 2. So I could rewrite 4 as 2 squared with an x. And then I could write 32 as the common base of 2 because 2 to the 5th is 32. And then I would have 2x equals 5 because I know I got my bases to be the same. And then x would be 5 halves. Well, we could use our third log law the same way. We could say, all right, I don't know a common base. Let's just say I'm drawing a blank on a test and you're like, I don't see that 2 goes into 4 and 32. Well, what you can do is change each side to its exponents. So I'm going to take the exponent of 4 and I'm going to look at the exponent of 32. Now I have to keep going here and realize that this exponent, we learned in the last lesson, was repeated. So that means I just have this many log 4s, or that many exponents. Another stupid way to remember it is exponents are no longer powerful. They fall down in front. All right, then how do I get this x alone? Well, I perform basic algebra, and I take the log or the exponent of 10, that gets me 32, and I divide it by the exponent of 10, that gets me 4, and this is where the calculator comes in. All I have to do is press that lovely logarithm key. Log of 32 divided by the log of 4, or the exponent of 10 that gets me 32 divided by the exponent of 10 that gets me 4, 2.5. Bingo. So for example 2, we couldn't use a common base. 5 and 42 don't have a common base. They do. You can manipulate 5 to get 42, but it's just too much work. So we're going to use our third log law. We're going to take the exponent of 10 that gets me 5, take the exponent of 10 that gets me 42, and then remember, this x is no longer powerful. It falls down in front because it represents a repeated multiplication. And so x is simply the log of 42 divided by the log of 5. Once again, calculator work. Log of 42 divided by the log of 5. Now, this one's not going to be a pretty answer. So they would have to tell you approximate. So let's approximate to the nearest hundredth and say that the answer is x equals 2.32. All right, example 3. A little different here. Is there a common base between 6 and 78? No, so let's just practice our logarithm third law. Hopefully by now, when you see this, you're just going to have the exponent fall in front, and I'm putting it in parentheses because it is a binomial. Take the exponent of both sides. Remember, it's still algebra. What you do to one side, you have to do to the other. And I'm going to solve right here. First thing I'm going to do is I'm not going to really reach for the calculator. I'm going to try and get x alone by using algebraic steps and not actual numbers, right? So if I divide through here by the log of 6, and I still have to get x alone, So that means I would add 3. And that's what I'm going to type into the calculator. Let the calculator do all the work. So this told me to take the log of 70, I already forgot the number, 78. Divide that by the log of 6. And then add 3. We're going to again round to the nearest hundredth, so it's 5.43. So x is approximately, we should really say, 5.43. So right up here, this really should have been an approximation also. Now you can check yourself. I'm going to come back here. And I'm going to take this answer and I'm going to store it to the x. And then I'm simply going to say, checking 6 raised to the x minus 3, and that answer better be 78, and boom, it is. Love my graphing calculator. All right, so of course we're going to have to be able to solve problems that arise from verbal word problems. That's really where we use logarithms. You'll see it a lot in AP chemistry or IB chemistry or whatever you take now. A biologist is modeling the population. As soon as we see the word population, your mind should immediately go to growth and decay. Population is always represented by an exponential equation. Something you got to remember for the regions. All right, when he first starts observing, there are 104 bats. So my initial amount, I always take down biology believes the bat population is growing at a rate of 3%. So growth means 1 plus the percentage. Based on this assumption, how long will it take for the bat population to reach 200? So we want to go to end amount of 200, and time is unknown. So if I were to write out this formula, it would look like such. All right, 200 is what I want to get to when I started with 104 bats, population growth 1 plus, and I don't know the time, right? This is the old f of x equals a base x. Initial amount, that's our base, and that's our time. So if I started this, I got to get to that t. So immediately my brain knows, since it's an unknown exponent, logs. I'm going to clean it up a little bit first because I'm trying to isolate that t. I'm going to divide by 104 to get rid of that 104. Now I'm going to enter in my logarithms. I'm going to work with the exponents of the left side. That t is no longer powerful, it falls down, and the exponents of the other side. Still, the t, the time, is not isolated, so I get that by dividing. And that is what I put into the calculator. Let's clean that up. They want me to take the log of 200 divided by 104. Notice I did not divide it out. I'm going to let the calculator do that and divide that by the log of 1.03. Roughly 22 years. So we're going to round that to the nearest whole. So we say the time is approximately 22. Wait, is it years? I have to come back up here and look. Per year. Yep, there it is. 3% per year. So that is 22 years. And the last one obviously is going to be a declining one. So again, I'm just going to look at, I know that exponential functions are in this form. We learned in last chapter that A represents my starting point. So let's see, stock has been declining at a steady pace of 5%. Stock started at a price of $22.50. So we're starting at $22.50. And the number of weeks, so that we know that this is weeks. I'm going to put a W there so I remind myself it's weeks. And we want it to reach $10. And our decline is 75%. Remember, because decay says we take 1 and we subtract the fact that it's decaying 5%. So that means we're maintaining 95%. Hopefully by now, we're going to try and isolate that W as unknown exponent as much as possible. And then, since it's an unknown exponent, we introduce the logs. To get that W alone, we have one more step of dividing about that log. Boom, and it's all calculator work from there. So it's a pretty easy chapter. So that was the log of 10 divided by 22.5. We want to take that answer and divide that by the log of 0.95. 15.8 weeks. It said round your answer to the nearest week, so we're going to say approximately 16 weeks. Yeah, well, if I see my stock going down that quickly, I'm going to look into why.